Hello, everyone. I'm just picking up here in this lecture where I left off in our live session before we got cut off by technical problems. But what I was working on was looking at the Schrödinger equation and finding a solution to it and then breaking that up into a space part and a time part. So I've got here the whiteboard as it was. Basically, hopefully you got to see at least up to this point what I was talking about, but here it is for reference. At the top, we have the Schrödinger equation. We said we're not going to worry about the potential at this point, so I'm just crossing that out and saying, in fact, what we use as a solution is right here in green. This is a solution to the Schrödinger equation when there's no potential. And that, in fact, we can break it up. We can rewrite it as just an exponential. And in fact, we can rewrite it as just one exponential times another. So one function of space times another function of time. And that's actually just for this particular solution, which was the solution for a specific potential, just a freely propagating wave. However, we're going to make this kind of assumption that this wave function breaks up into a space part and a time part more generally. We're going to generally do that. So I wanted to pick up there and just write out, if we do that, what does this original Schrödinger equation look like? And so there, let me go at it. So we can write, the point there is that if I take the derivative with respect to space twice, that only affects the space-dependent part. It doesn't affect the time-dependent part. So I can kind of pull that out. I can write, that doesn't get affected by the derivative, and I can write d squared psi of x dx squared plus v of x times psi of x times phi of t. And then, so I'm going to keep the potential for this part because I'm trying to do this more generally. And then I'm just going to have I h bar and then psi of x, it doesn't get affected by the time derivative, whereas the time part, of course, does. And then to make it clearer what's going on here, and to make it nicer looking, I can basically just divide this whole equation by the whole wave function, by both of these terms. And this sort of separation of variables and doing this with a differential equation, this is kind of a general mathematical trick. So you may have seen it already in math, but it's also something we're going to use a lot here in physics. We're going to take a function of several variables and break it up into functions of just a single variable at a time, and then do this thing where we plug it back in, write it out, divide by the whole thing, and see what happens. So I'm going to erase this part and just kind of keep that and come back up to the top here and just say I'm basically dividing by this entire space and time part of the wave function, because then what it looks like is that I get the minus h bar squared over 2m. I get, when I divide by psi times phi here, the time part here cancels, and I just get basically d squared psi. I'm not going to write as a function of time. Dx squared. Let me polish that. Dx squared, so I forgot my 1 over psi in there. Plus, when I divide with the potential term, they both just cancel, so I just get v of x there. Then I have equals I h bar, and then I have 1 over phi d phi dt. All right, and so what was the point of that? The point of that was that now I have a left-hand side and a right-hand side to this equation. And the left-hand side, everything is just a function of position, of x. There are no functions of time on the left-hand side. On the right-hand side, I only have functions of time. Nothing is a function of x. There's no x on this right-hand side. There's just time. So again, this is a general mathematical trick here. If I've got a function entirely of one variable equal to a function of an entirely different variable on the other side of the equation, then the only way that those things that can be true as a general, in general for all values of x and t, is if if each side is actually just equal to a constant. So that's the trick, and we're going to use that trick again and again and again. But what it means is let's actually focus on the right-hand side. That's very simple. That means IH bar d phi dt over, that's a t, not an f. Let me write this again. IH bar over, wow. All right. Over phi of t, I'll write as a function, equals d phi t. Okay. And in fact, since this thing is only a function of time, these derivatives, I've written them as partial derivatives, but there's only one variable here, so really it's the same thing as a regular derivative. I'm just going to write d phi dt. So I can separate this. I can move this around and basically solve this. IH bar dt equals phi d phi. Now I can imagine basically just integrating both sides. I'm sorry, I wrote something wrong here. This way I don't have to correct it in post-processing. I forgot, this is equal to a constant. Sorry, I forgot that part. This is equal to some constant. We don't know what that constant is yet, but we're going to quickly find out what it is. I'm just going to write a big C there. And like I said, I can write this as just regular derivatives. Now let me move these things around and get things on the same side. So I can write this as IH bar. Actually, I'm going to put the IH bar on the other side. I'm going to have d phi over phi equals C. I'm going to put the dt on the other side, and I'm going to, let me put the I over h bar on this side too. I've divided over I over IH bar. Sorry, now this looks more sensible. I can solve it. I can basically imagine integrating both sides and solving this. The right-hand side is in fact really easy. I can erase this stuff now. Because if I integrate dt with respect, I just get t. So I get c, some constant, times t over IH bar. Left-hand side, I have d phi over phi. If you think back to some of your calculus that you've learned, you might remember what that integral is. It's you're basically integrating 1 over of something. And the integral of that is a natural logarithm. So this is actually the natural log of phi. I potentially have an integration constant here too, because I'm doing integrals here. So technically I should have even another constant. Let me just call it a, because I don't want to, I already used c. But technically there could be, since I did an integral, there could be some integration constant that overall when I do that integration. This all looks a little mysterious, but let's fix this. We really want to just find out what is phi. What is this function? What is this thing as a function of time? It's some function of time, but what is it? Well, we've got the logarithm. If we then take e to the power of both sides of the equation, we can solve for that, and we can find that e to the log phi is just phi. So phi of t, I'm going to write that back in, is equal to e to the constant times t over IH bar plus a. And so really, I can actually write this as e to the ct over IH bar times e to the a. Well, e to the power of some constant is itself just a constant, so I'm just going to rename this Should I give it, maybe should have, I'm just going to call that B. And so I have some constant here, e to the ct over IH bar. And then what is this other constant, c? What are these constants? One thing I can check is that, remember, this right-hand side of the Schrödinger equation was supposed to be energy, the total energy, when we sort of went through the original derivation. Like this part on the left was p squared over 2m, then we had a potential energy, so kinetic plus potential equals total. So if we look at IH bar d phi dt, that should be equal to energy. And so let's check that out. What is IH bar d phi dt? That should be equal to, well, if we look at this function and just take the derivative, if we take d phi dt, it's an exponential, so we just get the same thing back with the coefficient brought down. So we get, we write the IH bar first, and then we get the c over IH bar, and then we get back the original function. And in fact, yeah, what we said originally with the Schrödinger equation is then the idea is this, that's supposed to be h bar omega, or the energy. So what we've learned is actually, well, the IH bars cancel. We've just learned this mysterious constant c, that's actually just the total energy. That's all it is. So we can write, and I've run out of room just before the end again. Let me sneak it up. No, I'll erase this. So we can write that phi of t is equal to some constant e to the total energy times time over IH bar. And actually, it's usually written a slightly different way, because remember, we said that E, like I said, E is h bar omega. So we can actually just write this as BE, the h bars cancel, and I'll get omega t over I. But also remember that I can multiply, that looks a little weird, but I can take both the top and bottom of this fraction over here and multiply by I. That's just multiplying by 1. But if I do that, then I'll get BE, e to the I times I on the bottom will give me a minus 1. And then on the top, I'll have I omega t. So that actually looks like just what we've already seen, what we sort of assumed in the first place, what the wave solution actually looked like. Remember, this was actually general. We got this, we didn't even use v equals 0. We got this in general just by assuming that the time part and the space part were independent. And so we've gotten this very nice result that there's some constant out front. This is just going to wind up basically being, ultimately, in the end, we need to normalize probability, because we want the integral of the wave function squared to equal 1. So so really the constant, this constant b, as I've called it here, just is basically whatever we need it to be for things to work out. And in fact, I've left out the time part here, and the convention is usually, you know, with the space part, we'll also get a similar constant out there. But of course, it's redundant to have two constants out front, and so it's, by convention, people usually worry about that constant when they do the space part. And so often, what you'll see people write for the time part is they won't even write that constant. They'll just say the time part is e to the minus I omega t, because they're keeping in their heads there that, yes, there's an overall multiplicative constant out front, but they'll take care of that when they take care of the space part of the wave function. But all we've assumed here is basically that the wave function divides into a purely space part and a purely time part, and we found that we, in fact, then can just say what the time part is. It really just depends on the energy or alternatively frequency of the particle, and we can just write out the time dependence. So that's that part, and then there's just one more thing. I actually want to go back to the original Schrödinger equation and put this in, and then see what the space part looks like. So what we've said, so that means we can write the original Schrödinger equation. And instead of looking at the space and the time part, we can just look at the space part. Plus v of x psi of x equals, and here I'm basically factoring out the time part from this whole equation, because here I'd have the IH bar d by dt, but when I do that, I just get the energy. I just get the energy. And all that's left is the space part. So this is what's called the time-independent Schrödinger equation. Independent, we'll assume that's spelled correctly. You can't read it, it's all a blob. That's the time-independent Schrödinger equation. And it's actually that, rather than the more complicated time-dependent one, that's going to be the starting point most of the time when we solve things. Because, like I said, we're mostly going to consider situations where things aren't really changing with time. And then so that simplifies things, because now we only have derivatives with respect to space, and we only have a function that's with respect to space. And so we just have a function of a single variable. We can kind of plot it, imagine what's going on, and we can look at solutions of this equation and figure out what's going on. So that's where we'll pick up on our next topic.